Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shops. I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is component testing. We're sticking with our component testing theme we've been doing for a while. And the topic today is cam and crank sensors. We're going to talk about how the different types of cam and crank sensors work, how we're going to diagnose them, how we're going to test them. We'll do a couple live walkthroughs on some functionality we'll use with the tool, scan tool, both the scanner and the scope, and so on. So the types of cam and crank sensors we're going to talk about today. There's four main types we're going to cover. There may be others out there, but these are four of the more common ones. So we have magnetic pulse generator. We have a Hall effect switch. We have optical sensors, light emitting diodes, and phototransistors. So if you ever heard of the OptiSpark system GM used, a couple other manufacturers use it as well. That could be used. And then also the magnetoresistive sensors as well. So first off, we'll start off with the magnetic pulse generator. Now, this is off this one happens to be off a Subaru. And what it does, it has, you see a cross section over here on the left-hand side. So we have the pinouts for the connector here. And it goes in and we have a magnetic core in here. So it's magnetic. And as pieces of metal will go by this magnet, it will generate a waveform out the back end. So depending on how it's set up and where it's set up will differ in how the signal gets sent out. But in this case, we have just a few. This is on the crank sensor right here, right? So the crank shaft sprocket is where this is. So this has a few little blips and it'll send out a blip. This will generally be an AC voltage output. So it works on induction, and it induces an AC voltage output out through it. So if you're going to see a connector for testing purposes, usually it'll be a positive and a negative. So it'll just send out an AC output. So you'll be on either side of zero. So this red line here in the middle, this dashed line, that is just that's your 0 point on the scope. So we see it goes above by a little over 10 volts, below by a little less than negative 10 volts, or a little more than negative 10 volts. And we see it just varies back and forth. Now, the voltage output will also be relative to the engine RPM on these. So the higher my RPM is, the further my amplitude goes up. So it'll actually increase the voltage, and the voltage will lessen as we lessen the RPM. Also, with all of these, if we're looking at it on the screen, as the RPM increases, of course, the frequency will increase as well. So those little blips will get closer and closer together the faster it goes, because it's going faster. On these also, the coil winding polarity is designed for that specific application. You can't reverse these. Remember how I said there's a positive and a negative? So you want to make sure it is connected the right way. I mean, sometimes you could get an aftermarket connector that's not pinned right or something like that. And it is a 2-wire sensor, as we said. It's a passive, induces this voltage output. Then we get to a Hall effect switch. So a Hall effect switch is going to be different. So it's going to be a toggling DC voltage output. So what you're going to see is a square wave if you were to test this on a scope, right? So it's going to be 5 volts, 12 volts, whatever the manufacturer had to design it or decide to design it. It is not an engine RPM sensitive signal. So as before with that AC output, the amplitude would change. On this, doesn't matter what the RPM is, the voltage is going to be very stable no matter what. So it'll stay at that 5 volts or 12 volts, whatever it happens to be. It's a 3-wire sensor requiring voltage feed and ground to operate. Some of them also have 4 wires and 2 output signals. So in this example over here, we have this connector, and we maybe have a power, a ground, and then 2 output signals, and they share the power and ground on that. Now this is on an older vehicle on a wow, name escapes me right now. Distributor. There we go. Distributor ignition. On a distributor ignition. So on a Hall effect switch, we're going to have this little window here that it goes through, and it's generating a magnetic field as everything else is. And we have these metal shutters, they call them, these shutter blades, go through this window, and as they disrupt that window going through it, it breaks the field there, and that's what generates the signal. So as it spins, it's going to go through this Hall window, and it is going to generate this signal with it. So let's look at an example on a real world car we were diagnosing. So this is on a distributor vehicle, and it was a 91 Ford F-250, and it had it was a 5.8 if memory serves me correctly. And the problem was it would stall over time. This could be running for like 5-6 minutes, it would stall. Could be running for 20 minutes, it would stall. Could be running for 30 seconds and it would stall. So it was really an intermittent stalling issue. And they suspected, well, maybe it's the crank sensor on this, right? So it could be very well be the crank sensor. So if we take a look, the easiest place to test on this vehicle, this is out of the guided component test off the scan tool. And we see it's got a 6-pin connector on the ignition control module. Right, so on these, it's got that little ignition control module. It plugs underneath the distributor. You've probably seen them before. If you've been working on Fords for any amount of time, you probably saw them. They're very prevalent back then. And we have these different signals. So we have the crank position signal, which they call the PIP. And then we have the spout signal, which is their spark out. That actually comes back from the computer. We have the IDM on certain cases. We have the run circuit, which would be power. We have ignition coil negative, and then we have the ground. So ignition coil control is going to be on pin 5, and then, of course, our ground is there. So pin 3 is IDM when vehicle uses computer-controlled dwell. No resistor is used. On others, with push-start systems, pin 3 is the start circuit, voltage high, key on engine cranking only. IDM and IDM resistor are tied in with pin 5 ignition coil. So that's not really related to anything we're going to talk about right now. But just know that there is a note in there. And then what we want to do is we want to be able to take a look at the ignition signal as well to make sure it's outputting an ignition problem. So it's not going to output an ignition signal, though, unless I have an input from the computer. And the input from the computer comes from the crank position sensor that also comes out of here as well. So you're going to see that crank position sensor signal come out, go to the computer. Computer sends out another signal to the module, and the module then sends out the signal to the coil. So it seems a little convoluted the way they do it, but it also allows the computer to control the dwell on the coil. So anyways, we decided to hook this up and see, why is this truck stalling? Is it the crank sensor? Is it the ignition control module? Is the ignition control module cutting out? Or is it something from the PCM? Is that signal not making it back? Since we knew we had, this is going out to the computer, this is coming back from the computer, and this is going out from the control module, right? So we have kind of that convoluted way of going about things. But there's my crank sensor signal. Now, another thing I didn't mention about Hall effects, which is pertinent to this case, is we want to make sure if we're observing a Hall effect signal, you see how it's just a square wave, in this case, it's a 12 volt. It needs to be switching through at least 90% of that range, right? So if it goes 0 to 12 volts, it needs to cycle through at least 90% of that. Because the computer is just going to consider the signal invalid if it's not high enough. So we want to make sure, and that's especially with Hall effect switches, they can be really susceptible to temperature. Like if it's really cold out, it might not send out the right signal. If it's really hot out, it might not send out the right signal. So if we're testing it with a scope, which would be the best way to test it, is to, you want to make sure you're just observing the voltage cycling through the right range. So here's my crank, here's my ignition, and here's my spout, as we said. So we wanted to do a recording. So we've started up the truck, let it record until it stalled, and then we stopped the recording, saved it, and we wanted to see what happened. So went for a couple minutes this time. Truck finally stalled. We zoomed out, And then we got the full picture of what was going on with the vehicle, and we wanted to see who fell out first. And I think it's pretty obvious that the ignition signal fell out first, way before the crank and way before that spout signal. So if we zoom in a little bit, we can take this, we use the detail controls on here, and this is our area of focus. So we're going to move that over, this little cursor. We're going to put that over there, and we're going to zoom in a little bit. And we can see here's where the ignition coil control, or the signal from the module, stopped. And then way over here, a little more than half a second later, wasn't that long of a time, but yeah, definitely a little more than half a second from where that spark cut out to where the engine finally stalled. Why do we lose crank signal? Because the engine stalled. Right? When it stalls, it's not turning, we won't have a signal. And then of course the spout can't come back because that's fed by the crank sensor. So we suspected it might have been the crank sensor. In this case, it was not a crank sensor, but it was a really good opportunity to showcase what you would see with a crank sensor signal, and that's how it controls that ignition. Everything's kind of tied together, right? So who fell out first, which came first, chicken and the egg type deal there. But definitely in that case, the ignition control module was not outputting that signal anymore. So that was a bad module in that case. I thought that was kind of an interesting little example. Another example of a Hall effect switch. So remember how we had on that one, on the distributor, we had it going through the window. Another way that we could have it is going to be the other way. So instead of adding material to the signal, we can take the signal or the material away from that signal. So here's just another example of a more modern design. This is on a 2011 Subaru. And we got the cam sensor here, and we can see how that sits in the hole in the timing cover. And then we can see how it has this metal wheel below it. So within this air gap, there's the sensor right there, and then there's a connector there, and then there's my metal wheel at the end of the cam sensor. So if we wanted to get better detail on that, it's going to look kind of like this. So here is the magnetic portion of this Hall effect sensor in this case, and it is going to generate a magnetic field, right? It's going to power, ground, and signal. So in this case, it generates a magnetic field, and I know it's a 2D magnetic field. I'm not a very good artist, but magnetic fields in 3D, but this is as close as we can get. But how this wheel disrupts this magnetic field, when it disrupts the magnetic field, it will send out a signal. So if we put this into motion, we can see every time that material gets taken away, it generates a signal. Instead of on the other way we had it, where if it had material going through that window, it would generate a signal. Could work either way, but regardless of how it works, whether we're adding material or taking that material away, we have this square wave that's going to come out. In this case, on this car, it's a 5-volt square wave. So that's just a couple of different ways it works. It depends on the manufacturer and how they decide they want it to work. So definitely worth a little bit of research too, to understand how that manufacturer decided they want it to work. Here's another one, and like I said, it's not all that common, especially nowadays. It's probably pretty hard to find these, but they are still out there. It's an optical triggering device. So GM had their OptiSpark system. Honda, I believe, had one. Nissan, I know, had one. So the way this works is you use LEDs. So inside the sensor assembly, we see this, the cross section right here. We have this optical disc that spins around on a shaft right there. As it spins, we'll have light on one end, or one side, and then we'll have a sensor on the other side, right? So as the light passes through the hole, it will shine on the sensor. The sensor will see that light, and it will generate a square wave based on how that light is flashing on and off. It's actually a fairly simple system, but as long as it was kept clean, it would work. And that was one of the major downfalls, is they had a lot of problems with coolant got into some of them, and they'd have ripping problems with that. And then it just has to be clean, and under a car, not all that clean, right? So it is, once again, a toggling DC voltage output, though. We do have that 5-volt or 12-volt square wave depending. It's a stable voltage output. Once again, throughout that RPM range, the voltage doesn't change. Does require ignition voltage and ground, and most units have 4 wires and 2 output signals because we have the 2 different areas on the disc. Here's just an example of where you would find that on, like this GM, we said, the OptiSpark system, right? So there's the pickup, and then there's the disc, and then there's the optical position sensor right there, and a bunch of other nonsense inside there as well. But that's basically where that sensor lies. So to look at that from a top-down view or from the front, we'd see that disc, and it has those two sensors there. So we have the high resolution disc, which just gives you a constant square wave with the same size, same voltage, kind of like a check for the vehicle. And then we have the low resolution, which has a small, medium, and large size, depending on how the manufacturer has it cut again. And that allows the computer to understand, well, what signal, what sensor am I on? So here's just an example on one of those GM vehicles. You see we have a small one, a bit larger one, then we have another small one, and an even larger one, a small one, and an even larger one. So depending on what, where it was in the firing order would tell it what sensor or what cylinder to fire. All right, so if this is cylinder 1, 8, 3, 6, 5, 4, 7, 2, and so on. So you'll be able to see how that goes round and round. See that. All right, then we have our magnetoresistive sensors. Boy, I'm just tongue-tied tonight. Typically, there's a 3-wire sensor. It does have that digital 5-volt, 12-volt output like a Hall effect switch. In this case, they are very sensitive to damage as well, and trigger wheel imperfections will cause sensor noise. So how this works is we have 2 magnets or two sensors on either side of this magnet right here, north and south pole. And my trigger wheel will come by this. It will run by number 1 first, and then run by number 2 second. There'll be a slight offset, and then it decides based on that offset where it was, and then it gives us an output signal. So it does all the math inside the sensor. Makes them a little more complicated. Also, in this case, the PCM does not supply 5 volts. The magnetoresistive sensor pulls up 5 volts and then toggles down to ground. So we want to watch that ground side as well to make sure that that is switching to ground quickly. Now, I want to talk a good amount about this trigger wheel imperfections right here. So if we have a problem with that trigger wheel, because that trigger wheel is a magnet as well. So it's magnetically encoded trigger wheel. So here's an example. This is a very common problem out there. Chrysler 3.6 Pentastar engine, and it's got dual cam. And the cam sensor here, as you can see in this detail, we have these magnetic encoder wheels, which are magnets, spinning magnets. And then we have the sensor right here, which reads both sides at the same time, and then outputs through a common sensor. So as I said, these are magnets. So when I have wear in my engine, such as maybe these roller rockers right there, running off the camshaft, right? We got the roller rocker, and we got the valve there, and we got the roller rocker, and we got the cam lobe. Well, when those roller rockers wear out, or anything else in the engine for that matter wears out, you see we got some good wear there. Where's all that metal go? Well, the metal goes into the oil, right? And where's all the oil go? Well, it goes around the camshafts, right? And including these magnetic wheels. So the magnetic wheels will pick up this magnetic material because it's iron, metal flakes, ferrous material, and it'll stick to the magnetic encoder wheels. That will cause all sorts of issues. Will cause codes, drivability problems, just from that metal sticking to it. And you may not know if you don't take that cam sensor out and look inside that engine and see where there might be a problem. Well, then you might not even know. And it might be as simple as cleaning it up. Of course, by the time it gets to that point, you probably have mechanical damage in there anyways. Probably going to be doing a lot of head work. But if not, if you catch it early enough, maybe you can save it. But definitely the magnetic wheels, that's the problem. It gathers that to it. Now, this is all with variable cam timing, and this is one without. And then there's a little article on that as well. Also, we need to remember, so that's on the Chrysler. Now, also, we need to remember on multiple vehicles, many vehicles nowadays especially, you also probably have to do some sort of an after repair, reset, relearn, something of that nature in order to reset the system. All right. So in this case, I am looking at a Camaro, right? 2014 Camaro. Crank position system variation learn procedure is also required when the following service procedures have been performed, regardless of a DTC. So if you replace the engine, you have to do it. If the ECM or body control module are replaced, you have to do it. Crank balancer is replaced. Crankshaft removal or replacement, even if it's just removed and replaced. Crank position sensor, disturbance or removal and or replacement. So even if I take it out to look and see if there's mechanical damage, that I need to do this variation learn as well. And then any engine repairs which disturb the crankshaft to crankshaft position sensor relationship needs to be done as well. So in this one, we're going to rev up the engine a bunch of times until it learns. So ECM monitors certain component signals to determine if all the conditions are met to continue with the crank position system variation learn procedure. Scan tool only displays the condition that inhibits the procedure. Scan tool displays the signals of the following components: crank sensor, cam sensor, and engine coolant temperature sensor. So you walk through the steps on the tool. It walks through, allowing you to be able to reset that system as well. So there's multiple vehicles where that is needed. All right, so where's the easiest place to find that? Now, if we have an intelligent diagnostic tool, or you have a VeriSedge, and you have current software on there, you need to have a data plan or subscription with the intelligent diagnostic tools. We have a quick link to the service resets and relearns. Now, you could otherwise go into the engine and find it that way. But if we go into service resets and relearns, that's a quick way to find them. So if we go down, we see multiple different things, reset timing, reset fuel trim. How about perform the idle learn procedure, right? So we can go in here, and then there's the crank variation learn, right, where we talked about that before. We could click on that, and that would walk us through that procedure as well. So even after I've diagnosed the crank sensor or cam sensor problem, I still need to relearn, reset the issue after the fact, or it's not going to run properly either. Right? So that is our schooling stuff. Now let's talk about practical applications with the scan tool. So here is my scan tool. And we just activate my car. I got a 2011 Subaru Forester in here. Now there's a wealth of information inside the tool already on cam and crank sensors. So let's go in. First, let's go in to actually look at manufacturer's information, right? So I'm going to go into my shop key over here, load my Subaru. Real time. There we go. All right, so here's shop key, and I have my vehicle loaded. So I'm going to check out the crank position sensor, so CKP sensor. And then let's say I replace it. So let's look at a little bit of information on there. Automatic. Okay. We're coming here, and we see a few different things. There's some TSBs on it. Actually, one of my other classes, I talk about a TSB that there is on the cam sensor. Air gap is too big. So if you want to check that one out, that's around. But let's look at let's look at remove and replacement. All right, so remove and replace and inspection. So this is kind of interesting. So they said measure resistance, right? Resistance test, that's pretty easy to do. They also give you a method with a scope. So manufacturers are saying you want to test these things with a scope nowadays. So there's just an example of a cam position sensor waveform, or crank position sensor, sorry, on this vehicle. This is 2011 Subaru. And we can see that there is the crank sensor information right there. So there's the scope patterns, what it will look like. And notice how it's on either side of 0. So that means it is that analog sensor we talked about at the beginning on this. So that is interesting that they have you do that. If you go to component operation, I believe is what it is. Yeah. So component operation, it gives us that side view of it. And molded consists of a magnet core, coil terminals, and other components as illustrated below. And then as it rotates, it generates a signal out to the PCM. So we see on this, we have teeth all the way around, except we have a gap here, and we have 2 gaps of the same size over here. So they call that a single gap and a double gap on this car. And then we have all these other smaller signals. So that's where it sends these signals out. These are the small ones. There's the double gap right there. And then there's a single gap right there. So half a rotation gets us either through the double gap or the single gap. Now that's important to know and understand if we're going to try and do some more testing on this that we're going to talk about in a couple minutes. Also important, I don't know if any other manufacturer is affected by this. I bet you they probably are. I've never seen one in person, but I know personally I have seen on a Subaru. In this example, if you remember earlier on in the class, I showed a diagram and it had like 5 teeth on it, right? They're very widely spaced and they have maybe 5 teeth all the way around. This one has many teeth all the way around. So that engine could still fit in that same car because it's the same engine block. They just decided to change the crank sensor logic on the vehicle. So if you put the wrong crank sprocket on that car, because they made a mid-year change around about 2004, they made a change where they went to this logic. So if I have an older car, that 2004 engine will still fit inside that car. And if I don't think to change that crank sprocket, that car's not going to start because it's sending definitely the wrong signal to the computer. The computer is not expecting that signal at all, and vice versa, right? So if I put a 2003 engine in a 2004 or 2005, I would have the same problem, right? Because I've actually seen that happen before. And all you got to do to fix it is just swap the crank sprocket, and it's fine, and everything will work. But it's just they changed that logic there, so you just got to watch out for that amongst at least Subaru. I'm sure other manufacturers are probably the same way as well, right? So that gives you a known good pattern there. And then if we wanted to come up here to my specifications, it actually gives me, which is really nice, a cam crank correlation pattern, right? So I have my crank position sensor here. I have my cam position sensor on the right side, cam position sensor on the left side, all in there. And here's what it's supposed to look like, right? So we got a gap, we got a blip, we got a hole, we got the double gap, the blip and a blip, single gap, blip, blip, double gap, hole, blip, and so on. So it's a combination of 4 different patterns going with the 4 different cylinders on the engine, right? So 1, 3, 4, 2, the firing order. So we'd see 1, 3, 4, 2, just like that. All right. Now this is a cam crank correlation. We get asked about how to do a cam crank correlation test on a car many times. There unfortunately aren't any presets in here, but we can go and examine one that we've taken off another car here. So let me just switch over to my ShopStream Connect here. All right. So this is off that same 2011 Subaru Forester. It's a real pattern off of one of those vehicles. Now I have my crank sensor here, and we can see it's got that analog signal. I got my single gap, I got my double gaps. And if I turn on channel 2, that's going to be one cam sensor. Channel 3, that's the other cam sensor. And then channel 4, what I did here was I added in a an injector, fuel injector, right? So what you want to do when you're trying to see how is everything lining up, you need to be able to trigger off of something. So what a good suggestion to do on tests like these, where I need to see one firing order, right? One instance of the firing order, 2 rotations of the crank. I want to be able to have some sort of a trigger point there to see, okay, here's where I'm lining up on cylinder 1. And then if I know the firing order, I can understand after that. You can use it for this, you could use it for ignition, and so on. You can use the injector, you could use an ignition coil, right? It just depends on what's easiest to access. In the case of this car, injector's right on top, nice and easy to get to. You just back road at the injector, and there's cylinder 1. Now, I will tell you there's a lot going on right here, and it's kind of hard to see. So what I want to do first is I want to change my setup here and change my view to do 4 windows on the screen. There we go. That's a little bit better. Now I can see a little bit better what's going on here. It's not all jumbled together. And that looks an awful lot like the screen we had before, right? Where I have my 2 cam sensors, my crank sensor. So now we're going to do a little bit of math. We got to figure out, is this on or is this off? What's going on with this? So in this case, I know it's a known good pattern. So I can see and I can measure. So we're going to go through a little bit of math. I know math is super fun and exciting, right? But math can help us when it comes to these types of things. We're measuring rotation in degrees and how far are they apart. So first off, let's go. I'm going to put cursor 1 right here, and I'm going to put cursor 2. I'm going to go back over. Well, there's one crank revolution right there, and there's 2 crank revolutions right there, right? So we know the crank turns twice every time we go through the firing order. Another way I can verify that as well, my injector fired there and the injector fired there. So that's the same cylinder right there. So one time through the firing order, 1, 4, 3, 2. There we go. Okay. So from there to there, I'm on pretty much the same part of the waveform, right? Little dip right there, little dip right there. So this tells me 136.88 milliseconds is how long it takes to turn 2 times. right? So now if I want to figure out, okay, so where is each, let's just call it 136 to make it easy, right? So call it 136, and let's do some math here. So let's pull up my calculator. So 136, and first off, let's divide it by 4. 34. So if I divide that by 4, I get 34. So that means 34 milliseconds happens for each stroke of the engine, right? So if I leave that over there, take number 2, and it should be right about where that gap happens again. And sure enough, 34.25 milliseconds. 34 milliseconds. If I move it again, we should have 68, right? 68. And if I move it again, that should be 102, right? 102, I believe that is. 102, right? 102 right there. So each of these is one of the strokes on a cylinder, right? So there's my 4-stroke engine. Next math we can do. So we go 720 degree crank rotation. So if we take that 136, divide it by, we know we got 720 degrees. 0.18, we'll call it 0.19 if we round, right? So 0.19 milliseconds per every degree of crank rotation. So let's see, how far apart is that to my camshaft? How far apart is it from the beginning of this event to my camshaft? How many degrees? So that's 2.49 milliseconds. 2.49 milliseconds divided by 0.19 gives me 13 degrees of crank rotation difference between where that crank sensor starts and where that cam sensor starts. So 13 degrees of crank rotation. So we know this is a known good. We already pulled it off a known good car. We know it's known good. So in that case, if I ever run across a known bad car, I'll know, well, if it's not roughly 13 degrees or so, I know I have a problem. Now, if the cam is advanced, it's going to be to the left. If the camera is retarded, it's going to be over to the right. So that could be stretched timing chain, could be the belt jumped if it has a belt, could be was installed incorrectly, right? Maybe the technician didn't even line it up correctly. I've seen that happen plenty of times before too. So you can diagnose some sort of a drivability problem just by being able to look, how do my cam and crank line up, just being able to test it that way. So we get a lot of questions on that. Hopefully that helps you out a little bit. I know there's all sorts of other ways to do it, but if we just keep in mind just a little bit of math, that can help us at least figure it out, and it really applies to any car. Now, some manufacturers do publish their specs with how far apart that is or how many teeth apart they should be on the pattern. So that makes it even easier when they publish that. So we can actually see, how far apart are they and such, and see how far it's off, right? And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.